With the great advances in today's machining techniques, it is now of utmost importance that component parts display much closer tolerances. Since high machine accuracy is necessary for long-running unmanned operation, a machining center integrated into FMS or FMC should be able to run stably 24 hours a day with great accuracy. We would ask you to consider which design features have the greatest influence on machine tool accuracy. Let's take the most difficult operation, a horizontal machining center carrying out stub boring operations by indexing the table 180 degrees. What difficulties are we likely to encounter? The main items to be machined on the workpiece are the spindle bearing housing, in which the spindle is incorporated, and 2 bar slide bores. High parallelism and accuracy between the bore centers are vital. The performance of this housing greatly depends on how high the machining accuracy is. Poor machining accuracy will give rise to component failure and other problems, some of which we will describe shortly. As you can see, this workpiece has 3 important bores. They are marked A, B, and C. These holes, A, B, and C, are bored from both ends of the workpiece. Mark these holes for boring as A1, B1, and C1, and then at the opposite end, A2, B2, and C2 like this. Using a stub boring bar, we machine A1. We then index the table 180 degrees and machine A2. The tools are then changed, and A2 is counterbored. The table is then indexed 180 degrees so that the counterboring of A1 can take place. The tools are then changed so that the machining of B1 and C1 can take place. And by indexing the table 180 degrees, B2 and C2 can be machined. Next, change the tools once again and counterbore C2 and B2. Index the table 180 degrees and then counterbore C1 and B1. Bores A1, B1, and C1 and A2, B2, and C2 should be machined to correct center distance. Also, A1 should be concentric to A2, and B1 to B2, and C1 to C2. Each hole to be machined must be parallel to the reference surfaces W and Z. In addition, reference surfaces X and Y must be paralleled. Moreover, each hole to be machined should be square to reference surfaces X and Y. Similarly, the bottom faces of counterbored holes A1 and A2 must be square to the bore, and also parallel with surfaces X and Y. In order to machine a workpiece to the required high accuracy, we wish to examine how errors occur when indexing the table through 180 degrees. First, the repeatability of machine axis positioning is poor. Secondly, the indexing accuracy of the index table is poor. Thirdly, the runout accuracy of indexing on the table is poor. Fourthly, thermal distortion has occurred to the machine. And fifthly, the center line of the spindle is not parallel to Z-axis movement. These are the possible causes. Then what influences will these errors have on the actual machining? First, let's think over what influences repeatability of positionings. It is absolutely essential to position the table, the spindle head, and the column accurately in order to machine to close tolerances. I repeat, absolutely essential. If repeatability is poor, high accuracy machining cannot be attained. Positioning can be made in rapid traverse, in slow feed, over a long distance, or over a short distance, or from a distance of a few microns. In each case, positioning must be made precisely as commanded. Now, as an example, let's take a look at the boring of A1. If you start from a point at which W face and Z face cross each other as a reference point, Z-axis direction and Y-axis direction can be positioned at a rapid speed due to the fact that A1 is a long way from the reference point. In this case, if the rigidity of the feed unit is low, or if there's any backlash, the slide will overshoot the commanded value. Then what if the machining were carried out slightly out of position as shown in the illustration? After the completion of machining of A1, the table index is 180 degrees, and A2 is machined. Then the error of the center with A1 and A2 is double the initial error caused at the first positioning. Now, let's consider this example further after we have changed tools and move from bore A1 to bore B1. In order to move from A1 to B1, both the X and Y axes move in a minus direction. And due to the fact that the Y-axis moves in an opposite direction to when it moved to A1, if there is any backlash or lost motion on the machine, positioning will be made with a shorter distance than the commanded value. On the other hand, the X-axis must move a short distance at incremental feed. If on a machine which has a stick slip, positioning will be made short of the commanded value. In this case, there arises an error in the distance between B1 and A1. The center of B1 and B2 will have an error equal to double the positioning error. Naturally, the bores machined under such conditions will not be parallel to the reference surface W, or concentric about the true axis of their bores. Thus, each hole, A, B, and C, has been machined without maintaining the proper relative positions of all three. We would now like to draw your attention to the indexing accuracy of the table and its effect on machining. For example, when machining a bore in the spindle head stock and gearbox from both ends by stub boring, the accuracy of the indexing table decides the concentricity of the bores. If the indexing accuracy of the table is not correct, first, X and Y faces opposing each other will never be parallel, for instance when face machining with a face mill. Further, X and Y faces will never be square to the pre-machined reference surface W. Next, if the opposing holes are machined from both ends by indexing the table 180 degrees using a stub boring bar, the bores A, B, and C will not be in line from each end or parallel to face W, and will not be concentric about the true axis of their bores. The runout accuracy of the table when indexing is of vital importance to achieve high accuracy machining. If the index table precesses while indexing, how will the machining be affected? This is what we call precession of the index table. This has a serious effect on machining accuracy. For example, when boring from both ends, the bores will not be square to the reference face Z fixed with the table. Thermal distortion of the machine greatly affects machining accuracy. Now, let's think about the column Y-axis that guides the up and down movement of the spindle head, and the table X-axis that moves the workpiece to the right and left. First, let's take the Y-axis. Due to the conduction heat and radiant heat generated from the spindle head, heat expansion occurs to the side of the column near the spindle head, developing into curved distortion of the slide. Therefore, in the case of usual machining centers guided by only one guideway on either the right or left side, the spindle follows a curved up and down movement. In this case, the position of the Y-axis will greatly influence the machining accuracy. Let's now look at the effect on our example of a wrong machining as shown in this illustration. Both holes B and C, which are positioned low, receive only a little deviation, while hole A, which is positioned high, receives a large deviation. In the case of machining after indexing the table 180 degrees, the concentric deviation due to thermal distortion will be doubled. In order to move the spindle up and down on a correct straight line all the time, with no influence by curve distortion caused by thermal distortion, the most ideal system is to move the spindle up and down, pushing and expanding the two guideways by roller pack bearings. Let us now consider the effect of thermal distortion in the x-axis. If you operate a machine continuously over a long period, a positioning error can be caused by thermal distortion of the ball screw base or base table. This positioning error will be doubled when machining by indexing the table 180 degrees, as we pointed out earlier. To minimize the influence of error by thermal extension of the ball screw, due to generation of heat or thermal deformation on the base table, it is necessary to compulsorily cool down the ball screw bracket where heat is generated most. Lastly, we would like to draw your attention to the problems which can occur when the center line of spindle rotation is not parallel with the z-axis movement. If the spindle is not parallel with the z-axis, for example, inclined within the horizontal surface, the machining position will alter according to the length of the tooling. Now, look at this illustration. At first, suppose that after hole A has been machined, the tool is changed to a longer tool, and holes B and C are machined. The pitch between the center of holes A and B will be increased, while on the contrary, the pitch between the center of holes A and C will be decreased. Under this condition, if the workpiece is bored from both ends by indexing the table 180 degrees, the centers of bores A, B, and C will not be concentric. Moreover, the center lines of bore A to bore B and bore A to bore C will not be parallel with each other. Similarly, in the case where the center of the spindle inclines within the vertical plane, the machining position will also be changed. As you have just seen, successful stub boring by 180-degree indexing requires a horizontal machining center that has been built to very exacting standards of accuracy. In this presentation, we have shown you some of the important factors of accuracy machining on the Machining Center. Today, more than ever, stabilized high machining accuracy over long periods of time, especially in unmanned operations, is extremely important. In addition to having a machining center with the correct design characteristics, another important factor to achieve high accuracy machining is to locate the machine in a satisfactory environment. Now, to conclude, let's summarize the important factors for high-accuracy machining by indexing the table 180 degrees. What are the important factors in high-accuracy machining, including boring while indexing the table 180 degrees? Repeatability of positioning must be high. When positioning, it is vital to position to the exact value required to avoid stick slip, etc. Indexing accuracy of the index table must be high. The runout accuracy of the indexing table must be high. The machine should be so built as to minimize the thermal distortion, and machining accuracy should be unaffected by the thermal distortion. The center line of the spindle rotation must be parallel with Z-axis movement.